Traditional web applications rely on stateful authentication. When a user logs in, the server creates a session and stores it in a database. Every subsequent request requires the server to query that database to confirm identity. At scale, this constant lookup process becomes a severe performance bottleneck. This split screen compares the bottleneck versus the modern alternative, the JSON Web Token. It packages user identity into a self-contained string, removing database queries. A JWT unpacks its three base64 URL encoded segments into a JSON header, a JSON payload, and a cryptographic signature. This structure removes the requirement for secure server-side session storage. Instead, the security of the entire system depends on the cryptographic verification of that third segment, the signature. To accommodate different security requirements, the JWT specification employs cryptographic agility. This allows the protocol to support multiple interchangeable algorithms for creating and verifying signatures, depending on the environment. When developers implement this agility without strict constraints, they leave the verification logic open to manipulation. Attackers can hijack the authentication process without needing a password or a leaked secret. We are going to analyze exactly how these cryptographic tokens are mathematically compromised and how to architect a genuinely secure verification system. The authorization server issues JWTs, and dozens of independent microservices must verify those tokens before granting access to data. In symmetric cryptography, or HS256, the exact same secret key is used to both create and verify the signature. But sharing that single master secret across dozens of services means a breach in one insignificant service compromises the entire network. This is why distributed systems require asymmetric cryptography, or RS256. The authorization server signs the token using an isolated private key, while downstream services verify it using a public key retrieved from a centralized key set. This establishes directional trust. Only the central server possesses the mathematical ability to create signatures, while downstream services can only confirm whether a signature is valid. To perform this check, the microservice reads the ALG parameter in the JWT header. This metadata tells the server whether to apply a symmetric or asymmetric verification equation to the signature. In this configuration, the server is allowing the token itself to dictate the specific rules for its own verification. Directional trust is fragile. Its security depends entirely on the downstream services strictly enforcing their verification rules against malicious instructions. Many JWT libraries are designed for maximum flexibility, meaning they dynamically route their verification logic based entirely on what they read in the token's alcutter. In an algorithm confusion attack, an attacker intercepts a token and performs three manipulations. First, they change the header from RS256 to the symmetric HS256. Second, they insert a new payload claim granting administrative privileges. Finally, they generate a new signature using HMAC SHA256, utilizing the server's openly published public key as the symmetric secret. When the server receives this forged token, it reads the manipulated header. Following the token's instructions, the server's logic switches to the HMAC verification path. It looks for a symmetric secret and blindly inputs the variable it has on file, the RSA public key. This exposes a mathematical mismatch. The HMAC algorithm treats the public key simply as a raw byte string, unaware that it was intended for an RSA asymmetric operation. Because the signatures align perfectly, the server accepts the forged token as authentic, granting the attacker the administrative permissions defined in the manipulated payload. The attacker has bypassed the entire cryptographic standard without ever compromising the private key. By weaponizing the server's architectural flexibility, they achieved a total system breach using only publicly available information. Algorithm confusion is part of a broader class of header manipulation attacks. In some naive implementations, an attacker can simply set the header to ALG none and strip the signature entirely to bypass verification. Another target is the key ID, or KID header. This tells the server exactly which key to retrieve from its own database to verify the incoming token. If that KID parameter is unsanitized, an attacker can inject malicious SQL statements or directory traversal paths directly into the header. This forces the server to execute unintended database commands or attempt to verify the signature against an attacker-controlled file on the local system. Relying on unverified metadata to drive backend logic fundamentally breaks the zero-trust model. However, even a perfectly verified token is useless if an attacker can steal it from the user's browser. Many developers store JWTs in local storage because it is easily accessible and persists across browser sessions. But local storage is accessible to any JavaScript running on the page. This makes the token a primary target for cross-site scripting, or XSS. A malicious script can instantly read local storage and exfiltrate the token. The alternative is an HTTP-only cookie. This flag mathematically blocks JavaScript access to the cookie, ensuring the token cannot be stolen via XSS. While more secure against theft, HTTP-only cookies introduce a different risk. This creates an opening for cross-site request forgery, or CSRF. An attacker tricks the browser into sending an unauthorized request, and the browser automatically attaches the cookie. To mitigate this, the HTTP-only cookie must be configured with a same-site strict flag, which prevents the browser from sending the cookie during cross-site requests. Ultimately, developers must choose between managing XSS vulnerabilities in their front-end frameworks or configuring strict CSRF protections on their endpoints. There is no mathematically perfect storage method, but HTTP-only cookies with strict configurations represent the most robust architectural compromise. This leads to the statelessness paradox. A self-contained JWT carries its own rigid expiration date, so it remains mathematically valid until that date passes. Instant revocation is nearly impossible. If a user logs out or their account is compromised, a stolen token remains active. The server has no memory of the logout and continues to verify the signature as valid. Securing this architecture requires 3 specific steps. First, you must hard-code and pin the expected verification algorithm on the backend, explicitly rejecting any algorithm headers provided by the token. Second, sensitive tokens should be stored exclusively in HTTP-only cookies to mitigate XSS theft risks. Third, to solve the revocation problem, the architecture must implement refresh token rotation. The server issues a very short-lived access token that expires in 5 to 15 minutes. This is paired with a long-lived opaque refresh token stored securely in the database and an HTTP-only cookie. When the access token expires, the front-end uses the refresh token to request a new one, happening in the background without interrupting the user session. When a user logs out, the server simply deletes the refresh token from its database, neutralizing any future attempts to generate new access tokens. This hybrid approach ensures that if an access token is stolen, the exposure window is limited to a few minutes. The purely stateless JWT is a myth. Secure implementation requires a deliberate spectrum of server state, precise cryptographic pinning, and